First keynote presenter is Dr. Tamitha Skov, who many of you I suspect know, has a fantastic call sign, WX6SWW. There's Tamitha. Very well known to most of us as the Space Weather Woman. It has a fantastic YouTube channel, has a huge social media presence. She's a credentialed space weather forecaster and has been telling us about space weather physics since 2013. So welcome, Dr. Skov.
Thank you so much. Thank you, all of you. I appreciate very much the invitation to come speak to you today. And I mean, from literally halfway around the world. In fact, where I'm from in Southern California, it's still Friday. It's Friday afternoon. So I'm looking to you in the future, right? One of the cool things about this particular conference is, right, you're looking at innovations in amateur radio. And I hope that by the end of this talk, if you take nothing else away, what you take away is that as you look into the rest of your time here and you see all of the innovations being done, know that the lessons learned in amateur radio and the future innovations that are being created in amateur radio right now are going to impact far more than just you in amateur radio and this field. You're actually going to be impacting a whole swath, a large swath of the population. And they're going to be looking to you for answers. Okay, you're going to be Elmers, not just to new hams, but also to other fields around the world. And especially during big solar storms. And with that, let me jump into it. Obviously, this is about space weather to a great degree. And even I'd only have like half an hour, so I can't give you a proper tutorial on big space weather phenomena, but we can talk a little bit about it. I decided I would just kind of boil it down to some of its fundamentals. And with the help of Jim Henson, I thought I'd kind of start it off this way. Hopefully some of you are familiar with the Muppets and the Swedish Chef in particular. And when we think of space weather, we have to think of space weather from the star to the Earth, right? From sun to mud. And when you look at the processes that occur, you really can boil it down to having two chefs in the kitchen. The first one is our star, obviously. And it's like this Swedish chef here with a bunch of eggs, throwing these eggs at Earth, right? With maybe good or bad aim, depending upon what particular thing is happening that day. But those are the solar phenomena. Now, a lot of people think that that's all you need to know about space weather. But in actuality, what happens is that when we get to the near-Earth system, we have a second chef. And that is our Earth's magnetic system. And that is like Mr. Chef here over number 2, who cracks those eggs that our first chef brings us and throws us, cracks them into a near-Earth skillet, scrambles them up, and then serves that mess to us on the ground. Okay, so that's kind of how you can think of it. That really are two chefs working in tandem to bring us the types of effects that we see here at Earth. Now, the types of eggs that we get, there's basically 4 types. Okay, we have solar flares, and I'll play this right here. You've seen this many times, I'm sure. This is what I call this when the sun screams. When the sun screams, boom, right there you go. This is basically a massless, this is just all photons, all light, but this is light going from gamma rays all the way down the spectrum to radio waves, and the radio waves, of course, are the ones that affect you, as well as lighting up our ionosphere. That can cause issues for us as well. But this is a dayside phenomenon. It takes 8 minutes for light to get to Earth, and it's basically what I call the sun screaming. If you can see the sun, you can hear it scream. But if you're on the night side, you don't have any impact from solar flares. Now, another type of egg that the sun throws at us are coronal mass ejections. These are what we call solar storms. You can see one here being launched out. This has material in it, so it moves much more slowly than the scream at the sun. These structures are the ones that as they blast out into the space, you can see them right here. Hopefully you can see this loop that continues to blast out into space here. This is actually material that is being ejected from our star. And as this takes days to travel to Earth, I'll stop it right here. This takes days to travel to Earth, so it arrives much more slowly than the solar flare. Plus, this material, these cause the storms that bring us aurora and can cause big nighttime disruptions, on the night side. Then they propagate over to the day side if they're really big storms. So these are 2 totally different phenomena, but a lot of people get them confused. But this one only affects the night side, and this one, well, essentially only affects the night side, and this one affects the day side. And yet people conflate them together. Now, the third type of phenomena that both of those first two drive are something called radiation storms. And you'll see it here. You can actually see a lot of those solar storms being launched out into space. And this is a coronagraph image. But pretty soon you'll see something that looks like a blizzard, right? And that is actually energetic particles that are traveling very, very fast. Not quite as fast as light because they are particles, but they're traveling faster than solar storms. But these things can actually cause issues for us at the poles. And anyone who notices DRAP or recognizes DRAP, there you go. There's a blizzard right there. Anyone who recognizes DRAP model and knows what these areas, when it turns red up at the poles, that is a radiation storm. We call them polar cap absorption events. Okay. And then the last thing is fast solar wind from coronal holes. You can see a coronal hole here. And fast wind from these holes actually they act very much like these big solar storms. They kind of have the same kind of effect. So these are the four types of eggs that our star throws at us. You got ones that, hit the day side, hit the night side, hit the poles. So it's kind of like a pie in the face, pie in the back of the head, and a pie on the top and a pie at the bottom. Earth is getting hammered all the time by all sorts of different phenomena in different ways. And how that happens is really through our second chef. So here is the near-Earth skillet. This is just part of it. When you look really close down to Earth, you can see particle motions all the way around. Particles will gyrate around these magnetic field lines, as you see here, and bounce from pole to pole. And then when they do that, they also go around and drift around Earth. So can you see how it looks a bit like someone scrambling up stuff? So every time an egg gets cracked in this near-Earth skillet, it gets scrambled up, and it basically makes it very complicated to describe to someone who doesn't understand how the Earth's magnetic system does this. It makes it very complicated. Sorry about that. To describe how the effects end up impacting us on the ground. Okay. And so now we plunge this stuff into the ionosphere. And really what the ionosphere is just our upper atmosphere. That is, it's basically a layer above our neutral atmosphere. And the reason why it's charged is because it is being bombarded by the sun's ultraviolet light. Now, this, not only is it being bombarded by the ultraviolet light, but there's also density and composition changes as you go up in altitude. And as the sun bombards this stuff and kind of, the rays can penetrate to different degrees, depending upon solar min, solar max, that type of thing. What ends up happening is that you get accumulation of charges, of electron charge, in specific layers, because the atmospheric chemistry in certain areas, certain altitudes, really predisposes that layer to collect charge. And then other times we have something called recombination that ends up kind of depleting that layer of charge. So because of that, we get the D, the E, the F1, F2 layers that you guys all know to use for things like skywave propagation. But these layers are very much affected by day-night changes, right? We talk about the gray line and how these layers can collapse as you pass through the gray line region. And also these layers are affected by neutral terrestrial weather from below, as well as dynamics from the mixing, the second chef mixing stuff and throwing stuff in the ionosphere, even during quiet times. But space weather can affect these layers in very dramatic ways. So you put it all together and you get a mess, literally. So if anyone is ever worried about why, wondered why it seems so hard to understand radio propagation, and gosh, this should be an easier field. No, it's not. And this happens even during the quiet periods. Okay, so now imagine inclement space weather on top of that. Okay, so with our particular cycle, we have actually had the opportunity to experience some pretty serious space weather. Hopefully everyone remembers not that long ago, actually there were two times, right? We had recently in October 10th and 11th, we had a big storm that was nearly a G5 level storm. That means the highest, that's the highest our scales go. Our scale goes from 1 to 5. And in May of this year, we actually did have a big G5 level storm. This is something we haven't seen in 20 years. And really how it happened is that we had a region that emerged on the Earth-facing disk that was originally two regions, but then a third region emerged in between them. And it kind of merged it all together. This movie will reset and you'll be able to watch that, the two separate regions merge. And see the third region in here? This thing actually just merged in this way and just collected, ended up causing these to be considered one big cluster. So the number 3664 took over right about May 8th. And this region, because it was so incredibly unstable with all this dynamics going on in here, fired 10 X-class flares in the span of just less than a week, including the largest flare of this solar cycle. It also caused the big G5 storm on May 10th and 11th. This is the largest storm we've seen in 20 years, and it's because it's the largest cycle we've had in 20 years. In contrast, or by contrast, we had no G5 level solar storms during the entirety of solar cycle 24. And in this cycle, we're still only up to solar max, and I'll talk about that in a minute. But that opens a lot of eyes, right? When you haven't had for 20 years a storm this size, and suddenly you have it, a lot of people who've never experienced a big solar storm suddenly wake up. Sadly, this is oftentimes what they think, right? It opens eyes to space weather, but not necessarily in the way we want. Everybody starts freaking out and panicking because they don't know what a solar storm is, and space weather is scary. And so you have and plus you have movies like this. Hollywood teaches us, of course, that space weather is like this. If you don't believe me, go watch Solar Attack, right? This is a movie starring Louis Gossett Jr., and you can tell it's about a CME. And of course, CMEs do this, right? All the time. We have people die from coronal mass ejections in solar storms all the time. So much so that we have pet names for them, right? Mega flare, kill shot, micronova, power grid destroyer, Armageddon from the sun, God's wrath, black swan. People basically think that these big storms are any space weather event that spells doomsday for Earth's weakening magnetic field and for all of our technology, and of course, ultimately, all life on Earth. Okay, let's step back, right? As amateur radio operators, you guys know this is crazy. I mean, yeah, it affects radio communications. It can cause issues for people, but it's not going to do this. So we need to get the public to settle down. But oftentimes this is people's first introduction to space weather, right? If they're not experts. But let's talk about the reality of this May storm. Okay, we call it the Gannon storm after Jen Gannon, who was an operational space weather scientist who died, sadly, unexpectedly, just a few days before the storm. She's a really sweet lady, and we miss her a lot. But you might recognize this. Some of you might even have a geochron. This is one of the new data products that is going to be coming out reasonably soon. This is, we have, of course, the amateur radio. Some of you guys get the amateur radio bundle. You're probably recognizing these lines from PSK Reporter. And they've even got you can't read it, I'm sure, but the frequencies here color-coded according to PSK Reporter. And then I've got an overlay here of basically what's called, it's kind of like KP. This is an HP 60, I believe I have this. So it's like the KP index, if you're familiar with it. It's a stoplight chart, green, yellow, red, green where things are quiet, yellow where we're going, uh-oh, and then red is storm. This is where the storm became a G5 level, was right about here. And you'll also see Aurora kick in. But as I play this, and hopefully it'll play without too much trouble, sometimes it gets hung up. You're seeing lots of radio propagation, no problem. I mean, even in your area, if you can see in the nighttime, this was going through the midnight sector at that time, and you've got lots of DXing in all sorts of different frequencies. Everything looks wonderful, but as we get into the wee morning hours, you will watch the aurora. You'll see it begin to build right here. Here we go. You can see it even in the K index. We're now in the red. And now watch within just a few hours, because you can see time ticking off here. Look at this. What happened? The radio propagation went away, right? Completely went away. Almost instantaneously is when that storm really picked up and hit the G5 level. Shows you how susceptible even to geomagnetic storms HF propagation can be and VHF propagation can be. Now, let's talk a little bit more about the dayside propagation. Usually solar storms don't, well, I guess I'll just start playing it. Usually solar storms do not cause problems during the daytime, but when they're really big, they can. And I'm getting a little bit of a hang up here. Hopefully this thing will continue running. What I've got here for you, is this one running? Hold on, guys. Yeah, it's running. Okay. What I've got here for you are two separate days, right, in your region, from about 10 a.m. local time to 2 p.m. local time. This is the day before the storm, okay? And this obviously is the day of the storm, during the day, okay? So this is May 11th. Look at how much more radio propagation you're getting the day before the storm. This one, when the aurora is close, look how little radio propagation you're getting. I mean, not when the aurora is close, but when we're at the strongest peak of the storm. And you look at the massive difference between the two. So even during the daytime, HF radio gets in trouble. And that's because aurora is just so incredibly strong during G5s in general, but during this particular G5, it was incredibly strong that it could really wipe out radio propagation even on the day side. Now, aurora for this storm was visually disruptive as well. And for those of you who like QR codes, this is a QR code to this page here. This is a Google map of the G5 made by Chris Wickland, and he is beginning to make these quite often. And what you're seeing, obviously, there are a lot of pinpoints, and each one of these pinpoints represents an aurora photograph or report, let's say, an aurora field reporter. And what's interesting about that is that they're color-coded. And if you can see, even down here, look at your region, the color codes, what they're showing is aurora that is basically the auroral oval. Those are the ones that are in green. As you can see, the auroral oval, when you look at all the kinds of aurora you can get, the auroral oval has lots of dynamics, and that's the aurora that you typically think of. But all of this orange and red, this is actually the SAR arc region. And this region with aurora is much more diffuse. It doesn't have a lot of the discrete undulations and sharp lines. And so what's neat about this is that the aurora photographers are beginning to understand how different aurora end up showing up on a global map at what times. And that becomes really important because the aurora photographers, they can see the type of aurora that you guys hear, right? When you do auroral propagation, you hear auroral propagation. But the question then becomes, if aurora photographers see all these different types of aurora during these big storms, well, might amateur radio operators hear different effects when they do auroral propagation, depending upon what aurora they're doing their propagation through? So it asks really interesting questions of whether or not there's some synergy there and we can learn from each other. And that becomes super important because the Gannon G5 storm didn't just cause beautiful aurora, didn't just disrupt HF signals. It disrupted GPS. And worse than that, it disrupted the agricultural community. In fact, back on the 10th, John Deere had to put out multiple alerts. And I'm not asking you to read all this stuff, so don't worry, I'm just going to give you the kind of a run through. They put an update out on the 10th at 5 p.m. talking about GPS issues. Then they had to update it at 6:30 because they found out that their RTK, which is a correction network, was also having problems. And what this meant was, and then they asked people to switch to, if they had it, access to their Starfire networks, which were satellites up in the sky. So the RTK network basically it's kind of like having a repeater, but it's a repeater located on your property. And so you get your GPS signals, but then you also have the RTK repeater that gives you correction values for your farm, so you know better where your geolocation is, because they have to get these rows when they're planting really precise. And so when you switch to Starfire, the SF2 and 3, that is satellites beaming down signals. Instead of using your repeater, you're using satellite signals that has access to a huge network of these repeaters all over the globe. And believe it or not, even the Starfire, as of Saturday morning, even the Starfire had problems. So they said, we strongly advise you to keep an eye on your guess rows, because people were having errors of 10, 20, 30 centimeters off, and that's just non-tenable. And in some cases, some of their planters didn't even work. And considering this was like a critical day for planting corn, at least in the United States, it was a huge eye-opener to the agricultural industry. And when John Deere ended up writing their final assessments of this stuff, they said, realize that when you head back into these fields to side dress, spray, cultivate, harvest over the next several months, the rows and things that you guys planted during inclement GPS, during basically this G5 storm, the rows aren't going to be where the tractors think they are, where your system thinks it is. So it's going to be difficult, if not impossible, for you to do certain things this harvest season. Blew my mind. I think what really got me was an agricultural dive when they said, if anything came from this, it's the importance of being proactive in protecting our food system and having a response plan in place to avoid large-scale disruptions. Can you believe this? So of course, I'm now working with people in agriculture here in the States. But it made me think, what is precision farming in the Australian region? And this includes Tasmania and New Zealand. And in fact, guys, agriculture is a $50 billion a year business. Huge. And smart farming counts for almost 6% of it as of 2023, and it's growing at almost 14% a year. Okay. And smart farming means drones. Look at this drone. Do you see that's a person? She could ride this. It's like a small horse, right? Here's soil management. You can make what they're called yield maps. You need GPS for all of this stuff. Water management with automated irrigation. You need to, again, be able to use yield maps to know where to water more or less. Livestock management, you need GPS. And then our favorite, precision farming, that got us all into this mess. Where do you drop your seed? How much timing do you need? How tightly do you need to make your guess rows? And even harvesting with combines. They need to know the location of their systems, especially if you're digging peanuts from under the ground. So it's a massive thing, and it's growing. This last bullet here says, in Asia Pacific, in Australia, the smart agriculture market is projected to lead the regional market in terms of revenue by 2030. In fact, even more recently, Horizon did a research about Australian smart farming. Look at this drone. Look at it spraying. Have you ever seen a drone this size? Right? It needs GPS. They're saying that the smart agriculture industry is going to be $3 billion by 2030. And it's growing even faster than the other report at over 14%. It's, in terms of segment, it's going to be the largest revenue generating agriculture type by 2023. And that was a few years ago. So it's exploding. So you can imagine that people are blown away when they get this G5 storm and everything just stops, right? Because you can't have that during harvest season or planting season, which is actually when these storms are the worst. And in actuality, this solar cycle really is just average. It was cycle 24, the last cycle that we had, that was the anomaly because it was so quiet. We're going back only to cycle 23. You know, you can see the sunspot number here. This is over time. This is where we are. We're essentially at solar max and solar cycle 2025. And we've seen sunspot numbers this size back into cycle 23, but it sure isn't anything close to the biggest we can get. And you should see cycle 19 that's on this side. Some of you guys probably remember cycle 19, right? Where flux was, solar SFI was way over 300. So we're just getting started with this stuff. And the agriculture folks are like, well, we don't know we don't know what's wrong with our signals. We have this kind of topology around the ground. We have these mountains in the way. We have this type of tractor. We have this type of antenna. We have this type. Does it sound familiar? Where everybody has different equipment and everybody's experiencing slightly different problems and they don't know where to start. And believe it or not, if you want to get a really accurate view of where our forecast is heading, we are about in here. So we've passed solar max. This is the Linker Space Scott McIntosh crew prediction. We are already coming into the declining phase of the solar cycle. And the declining phase may be much more active than the ascending phase because this is an odd cycle and it's the way it couples to the intergalactic field that causes which phase of the cycle to be more challenging. So are we done with G5 storms for this cycle? Likely not. And as you're probably recognizing, space weather impacts many communities, right? You guys are what I call you basically on the front lines of space weather. You know more about space weather impacts than any other community because you've dealt with it for so long. But these guys now, they had no idea. They cruised to become, popular during solar cycle 24. And now they're getting their first taste of space weather, and they really don't know what to do when it comes to signal propagation. So you recognize if we boil down those communities, right? If I take a look at these communities and I boil them down, okay, into some big segments, we kind of get something like this. We've got amateur radio, right? That's you guys, right? GPS operators, that should be pretty obvious, right? Storm chasers, okay, because some storm chasers, right, have amateur radio operator licenses, right? You see the connection there? And aurora chasers, okay? A lot of connectivity. Let's start with connectivity here. Amateur radio operators and GPS operators. Any of you guys do geocaching? Maybe emergency services? Maybe do hurricane watch nets, that type of thing, that maybe work with some of these people, right? That's easy. What about aurora chasers? Well, that's easy too, photography, right? Half of the aurora chasers came from the storm chase arena, right? But you guys have lots in common when it comes to space weather. Now, what about connectivity here? Well, aurora propagation. You guys hear picket fencing, they see it. They actually call it picket fence when they see that certain type of aurora. It looks like little picket fences, little green picket fences. So it's amazing that you have the same kind of idea. Amateur radio and storm chasers, well, Skywarn, at least in the States, right? You have to be an amateur radio operator in order to be a member of Skywarn. You have spotter networks, you have hurricane watchlets, like I said before. GPS operators and storm chasers, well, search and rescue, right? Certificate of authority operations to be able to deal with public safety, search and reconnaissance, that type of thing. So again, drones. And then aurora chasers, there's a lot of them that are drone enthusiasts as well. So you have aerial astrophotography and geolocation. So you're a highly skilled super community when you add all of this expertise together, and you're connected by your expertise. Because you could probably, if I had more time, I would be polling you and asking how many of you amateur radio operators do geocaching or fly drones, or maybe you go take an aurora picture from time to time, and you'll find that there's quite a few, or are storm chasers. But you're also a highly skilled super community connected by expertise and weather, right? Because aurora chasers and GPS operators, you have to deal with signal scintillation and UAV drift errors all the time when it comes to inclement space weather. GPS operators have to deal with collision avoidance and loss of satellite lock when it comes to the storm chase community, because that can put people in jeopardy, right? If you don't want your drone flying around erratically, you could hit somebody. Amateur radio and storm chasers, it comes to HF signal disruption and radio blackouts. And then the famous picket fencing, like I said before, and night side signal disruption. So really, this is where space weather and terrestrial weather collide. And this super community really has so much expertise that we can use to help each other learn the lessons learned and grow. And of course, the amateur radio operators lead the over-the-horizon detection and analysis arm of the super community, because you guys can see over the horizon before aurora photographers can even know what's going on. But aurora chasers lead the storm watch and public outreach arms of this community, because aurora pictures are beautiful, right? And they can see the whole structure of the aurora, the whole oval, where you guys just kind of pierce through part of it and go down in skywave anyway. But let's take the latest here. Let's not take GPS operators. Let's do the new one, precision farming, right? These guys have no idea. At least you guys have some clue, but they have no clue, right? I've already talked to one who's thinking of becoming a ham radio operator, simply because it will inform his precision farming, and he has to demand a call center for a well-known tractor and smart farming company. So he's thinking of becoming a ham because he feels that he might actually learn something about space weather and radio propagation. And guess what? Same with the storm chasers. A lot of them already are. And a lot of aurora chasers are beginning to recognize this. And I don't know about you, but I love that new ham smell. So parting words, the face of space weather is changing. We are opening new eyes right? Not just this G5, but even the October G5 or near G5, that actually opened a lot of eyes in the agricultural community as well, because they had, again, disruptions. This time it affected the peanut farmers, seems kind of silly, but it affected the peanut farmers because they have to harvest their peanuts and know very precise location, as precise as they needed to know during planting. So luckily, citizen-driven partnerships are growing. We are seeing these super communities growing. You just saw how Chris Wickland is doing these maps. He's doing a map for the October event as well, with even more information in it than the May G5 had. And we're becoming this super community, right? And amateur radio operators play a critical role in this super community. You guys lead the over-the-horizon detection and analysis branches. And the precision agriculture community is only one that will be looking to amateur radio operators for insight. You guys truly are the Elmers for the incoming members of this super community, and it's only going to grow. So again, as I mentioned earlier, as you go through the rest of this conference, take that in mind, that you're not just looking at the innovations in amateur radio for amateur radio's sake. You may be serving a much, much larger community than you could possibly imagine. And if you want to know more, help learn. We offer courses at Millersville for space weather. You can reach out to me if you have questions. You can reach out to me any of these places. I respond. I'm sometimes a little bit swamped, especially during inclement space weather, but I will get back to you, I promise. So yeah, feel free to reach out. I'd love to hear from you. And that's it.
Fantastic, thank you, Tamitha. And I'll just comment. You made reference to the G5 event and the aurora down here in Tasmania, and it didn't matter where you looked, you saw aurora. It was off the show, absolutely off the show. Now, questions. We've got roving microphones. We'll just hold your question until the microphone gets to you.
Sure, I'm here. I'm just going to pin you guys big so I can see you. All right, cool.
Okay, we ready? Rex.
Tamitha, I really enjoyed your talk, and there was one little clue I got as you went through to the question I'm going to ask. So over the last 18 months, while this cycle's been building up, we've been monitoring the aurora here in Tasmania using the digital mode Q6515C. Now, the advantage of that mode is you can measure the Doppler of the aurora. And
I love it.
What we found is, prior to roughly midnight, my friend here actually suggests it's magnetic midnight, we get a positive Doppler of about 400 hertz at 2 meters, and after midnight we get a negative Doppler of about 400 hertz. Now, that Doppler can persist for up to 8 hours before and after magnetic midnight. Now, clearly, that Doppler is far greater than you could get by just the advance or retraction of the aurora. And what our feeling is, it's related to these little plasma circles that you had in one of your diagrams spinning, and it's like we're hitting a sort of a water wheel in the horizontal dimension and getting much larger Doppler, which changes from one cell to the other after magnetic midnight. And we wonder if you can explain this.
Well, I can speculate, because I am not an ionospheric physicist by trade, and I am not a magnetospheric physicist by trade, but I almost am. But I can speculate on several different mechanisms. I think what really matters is actually being able to dive in and see exactly what latitude you're at. And let me ask you a question back before I speculate. Is this only during this one particular storm, or is this during lots of storms? Is a repeatable phenomenon?
It's quite repeatable. I think we monitored something like about 12 storms over 2023. The aurora actually comes and goes, like it pulses, on a time scale of hours. So
Right.
when we plot all of these together, we see this trend. So it builds up from all of these different auroral events.
Right.
I can
Understood.
send you a lovely graph at some stage.
I'd love that. You do like a superposed epoch analysis. That's a very,
yeah.
that'd be wonderful. I'd love to see that. What I immediately go to are flows, electron and ion flows, and because you're seeing a switch across local midnight, and I am assuming it's going to be magnetic midnight. It doesn't make sense to me that it would be a geographic midnight, and the only reason why I'm concerned, I mean, I would think electron and ion flows because they do go opposite directions as you cross midnight. My only concern about that is that I would think those flows would be too high. I'm kind of surprised to think that they could be that far down, especially if you're seeing them during weak storms as well as strong storms. But that's where my mind goes right away, just because of your crossing of the local magnetic midnight. And do you have, for instance, what level of storms have you seen it when the storms are really, really quiet? Have you seen it when it's just been substorming, or does it have to be a big geomagnetic storm for this to occur?
Yeah, we have to see the auroral oval, on the NOAA diagrams reach Tasmania.
Okay. I wonder what you're actually seeing. If you're seeing that on the ovation diagrams, that is actually quite okay. Maybe I'm now beginning to understand when you look at those ovation diagrams, they are underrepresenting the aurora. Likely the oval is already past you and is passing over you, and you may be on one side of the oval, and then as that auroral passes over you, it goes to the other side, because just in the rotation of Earth, that oval is tilted, as you likely know. And so as it rotates over you, you're probably seeing one side of the auroral oval from the outside, and then maybe possibly from the inside or from another angle. And that in of itself, or it could just simply be dawn and dusk, right? Because the whole oval itself is rotating. So just like the sun and the moon, aurora rises in the east and it sets in the west. So in your case, it rises in the southeast and sets in the southwest, right? So you may actually be watching it coming towards you as it pre-midnight. And then at midnight, does the Doppler shift go to 0? And then as you pass to the west and the auroral oval is moving away from you, is that when it picks up the opposite direction?
That's right.
Yeah, that might simply be the feature of a dawn dusk kind of effect, where you're looking at aurora rising and then just the rotation of the Earth. The aurora rises and then it sets. In other words, it comes towards you and then it moves away from you in that sense. And I'm talking the whole thing. I'm not talking about a substorm coming where the auroral oval expands and contracts. I'm not talking about expanding and contracting. I'm just talking about the natural, because of the tilt of the Earth's magnetic field relative to the geographic, our geographic equator, that will cause the auroral oval to tilt over you and then around. So it comes toward and then away. Does that make sense?
I think I better send you the diagram and we'll see where we go.
Yeah, it'd be nice to see. It'd be nice to see, because that's part of the problem, is I need to be able to see and ask you some questions.
Okay, thank you.
You're welcome.
Okay,
It's a tough question.
We've got one quick question. Time for one more quick question, if we've got one. Anybody? Okay, we'll get a microphone to Mr. 3BFG. There we go. Peter?
First of all, Tamitha, your scene every week on the Melbourne amateur TV repeater, so you're very
you so
well
much.
known in Melbourne. You haven't mentioned aviation and non-precision approaches in IMC, where you can't see anything and you're relying on a GPS to actually get you to the end of the runway.
Right. And that one of the reasons why I didn't focus on that today has more to do with the fact that that's a bigger issue, a much bigger issue when it comes to radio bursts. And it's a bit more complicated than just big solar storms. Big solar storms, luckily for the aviation community, especially commercial aviation, the inertial reference units that they have in their the boxes that they have in the planes are, I mean, they're $1 million units, and they have extremely good accelerometers and I forget what the other one is. You have an accelerometer, and then one gets the rotational, like a fiber optic gyro or ring laser gyros, stuff like that. And I think they're moving on to even better ones now. But those can handle a poor GPS or a loss of GPS lock for half an hour to an hour before they even begin to deviate. So it's a lot easier for them. But precision approaches, right, where you get the vertical dilution of precision being pretty bad, that's when WAS kicks in. That's when core, the high cadence systems kick in. And for the most part, they do pretty well. Where, even during solar storms, where they have a problem is when you get a radio burst that's up in the gigahertz range during big solar flares. And depending upon where the sun is in the sky, that can cause other issues too. Because we've had, we had a big event back in 2006 in December. We had another big event in 2015 in November in Sweden. But it's oftentimes either when the sun is at zenith or when the sun is near dawn and near dusk, right, near just above the sky, because it's now in the line of sight of the ground-based radars as well. So that's a complicated thing, but we also have big issues when it comes to aviation, but just not from a G5, if that makes sense.